Hello guys, how you doing? Today is the third session of chapter 3 of Fluid Mechanics 1. The title is F is equal to ma normal to the streamline. So follow me with the whole video. So as I already told you, today's session title is F equal to ma normal to the streamline. It is from section 3.3 of chapter 3 of Fluid Mechanics 1. Before keeping on the instruction, I'm going to introduce myself. My name is Amir Raza Talaqat with the email address of amirrazatalagat@gmail.com. Please don't hesitate to ask me about anything about fluid mechanics, or you can comment your questions in the comment section of this video. So, I hope you have already watched the previous sessions because we have discussed about the free body diagram of the force exerting on a flowing fluid particle. Let me just see. Yeah. In this session, we're going to talk about the forces exerted on a flowing fluid particle normal to the streamline, which is more applicable in a devastating low pressure region at the center of a tornado, which is taken from the Newton's second law across the nearly circular streamlines of the tornado. Based on the free body diagram in detail, we are having this equation. As we are having the centrifugal acceleration, this is the summation of the forces along the normal to the streamline is equal to MAN. AN itself is regarded as V to power 2 over R. M is derived as density multiplied by the whole volume, and AN is V to power 2 over R, which we are having 3.8, equation 3.8. It represents the normal component of whole forces exerted on the flowing fluid particle. As you see here, we are considering this direction. So let me just the main reason why we are considering the forces normal to the streamline is owing to the fact that sometimes we are not able to comprehend the actions that are happening on the flowing fluid particles along the streamline, but also we can just resolve the whole matter in the normal direction. So as you see here, we are having the component of delta Wn in this direction, which, if we regard it as here, is delta Z over delta N is equal to cosine theta, which is delta W is delta Wn is equal to minus delta W cosine theta, which we are already having it here. As you already know, we are having the W as minus gamma delta V. Because we are having delta minus delta W, we are having minus gamma delta V. The interesting thing is that when we are having theta equal to 90 degrees, which means the whole stream is along the horizontal line, along the streamline. We are not having anything to do with the normal weight component. Similar to previous session, when we consider the center location of the particle as P, the pressure of that location, as we go down, we are having P minus delta Pn multiplied by delta Z delta N. Yeah, delta S delta N, excuse me. And when we go over, we are having P plus delta Pn multiplied by delta S delta N. So doing the whole calculation, we're gonna reach this minus 2 delta Pn delta S delta Y. Doing the Taylor expansion rule, we can just identify the delta Pn equal to rho P to rho N multiplied by delta N over 2, because we are considering at the middle of the particle here. The half goes to this, the half goes to this. Apply delta Pn to this part, we are having it as minus delta P over N delta V. So having the combination of this part and this part, we're going to reach to net force of the whole forces along the normal line in the equation 3.9. As I already told you, we can just describe the cosine theta as dz over dn. By just replacing it, we're going to have the equation 10.10a. As you already see, the net forces along the normal line is the combination of the pressure gradient as well as the weight force along the normal line. This means that by having the higher amount of density or velocity, or having the smaller curvature, we can just have the larger force exerted on a particle in a motion. If we just not regard the gravity for gas flows, we can just have it as equation 3.10b. This is more applicable when we are just analyzing the tornado phenomena. When we are having a tornado, the direction to the center of the tornado is regarded as the positive direction. To the outside is regarded as minus direction. So when we are going outside of the tornado, we are experiencing more forces on us because of the minus there is here. Minus and minus range of the curvature causes more forces, as we are having minus to minus, which is equal to plus sign. Minus sign compensates the minus side here because we are going outside the curvature. As a result, we are having a plus sign of the force. So I hope you are not stuck in a tornado, because if you do, you're going to be moving around all of the time. So we are having a good example about pressure variation normal to the streamline. I'm going to have it solved for you in the written text. So follow me with it. So welcome guys to the problem solving of example 3.3, which is titled as pressure variation normal to a streamline from section 3.3 of chapter 3. The question wants us to determine the pressure distributions for P equal to PR for each given that P is equal to P0 at R is equal to R0. The whole question is, as shown in figure E3.3, A and B are two flow fields with the circular streamlines. The velocity distributions are as this. V is equal to R, VR is equal to V0 divided by R0 multiplied by R for case A, and for B is equal to VR is equal to V0 multiplied by R0 divided by R. V0 is the velocity at V0 is at R equal to R0. As you know, we are analyzing the steady, inviscid, incompressible, flow along a streamline. So we shall be taking the equation 3.9 about Bernoulli equation along cross line of a streamline. So we're gonna have it as this: rho P is equal to R, rho P to rho R, minus gamma cosine 0 equal to rho V over 2 power 2 over R. As we were taking it at vertical direction, the theta is going to be equal to 90 degrees, which cosine 90 is going to be 0. So this term omits automatically. We're having it as rho P to rho R is equal to minus rho V2 power 2 over R. We have a consideration here. The radial coordinate that we're studying is equal to rho to round n minus rho to round R. So we can have it here. This is rho R, and take it as this: rho P to rho R equal to plus rho V to power 2 divided by R. Applying it to equation A of velocity, the pressure gradient for A is going to be equal to rho R is equal to rho V0 divided by R0 totally to power 2 multiplied by R. And for B, rho P to round R is equal to rho V0 R0 to power 2 divided by R3. As you see, the pressure goes up and the velocity goes down according to the Bernoulli equation to remain steady. So we have it as this for integration. P is equal to P0 and R is equal to R0. Taking the integration from 0 for both of them, for the equation is going to be like this: P minus P0. I've just taken the integration is equal to rho V0 to power 2 divided by 2 R divided by R0 to power 2 minus 1. Yes, yeah. I've taken it as this from this and substituting these amounts. For state A, this is going to be equal to P minus P0. Excuse me, let me just bring it up. P minus P0 is equal to rho V0 to power 2 over 2 minus R minus 1 minus R0 to R over R to power 2. For the B status, we have it as it's not really easy to extract the equation out, but it is available on the picture. Welcome back, guys. Split image of previous session. We are just interpreting anything happened in one dimension. So we can just describe the round P to round N equal to dP over dN. This is the Bernoulli equation happening along the normal line, actually, which is equation 3.11 integrated from equation 3.10a. Guys, when as we are analyzing the whole term based on the incompressible flow, we can easily integrate the density here. However, pay attention to that. However, we cannot just easily integrate this term, V to power 2 over R, because R is comprised of two directions of S and N, and also the V. We can't just integrate it easily owing to the fact that we have to go through the details of the variation of velocity vector as well as the curvature. If we do know the concepts and the variation trends, we can integrate it at the moment. So the total Bernoulli equation term in the normal direction is P plus rho integration of V to power 2 over R dN plus gamma Z, which is equal to a constant across the streamline. So based on this equation, we're gonna comprehensively grasp the sum of pressure, elevation, and the velocity effects is constant across the streamline. So this is the end of third of session for chapter 3. I hope you have figured out everything easily. As I already told you, please don't hesitate to email me or have your questions in the comment. I try to give you the answers as quickly as possible. And most importantly, please subscribe to the channel in order to get the notification of following upcoming instructional sessions. I bid you all farewell. See you in the next session.